Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A Level Chemistry, Unit 5, Section C for October 2021. I already did the videos for Section A as well as that of Section B. I will put them in the description box of this video so that you can be able to access them as well. So please do not forget to check them out. Let's begin with this question. So question 21 says, organic molecules are an important source of color both in the natural world and in a wide range of industrial applications. Curcumin contributes to the yellow color of turmeric spice and is used as an additive in cosmetics and foods. It has been suggested that curcumin can act as an antioxidant and anti-cancer agent through reactions with free radicals and proteins, and may also inhibit Alzheimer's disease by complexing to toxic metal ions. So here we see the structure of curcumin. Please do not be scared by this structure. They will not ask you very complicated questions. So here they say, azides are synthetic compounds that do not occur naturally. They can be used to color textiles such as cotton. The acid-base indicator methyl red is an azide. So here they've given us the structure of methyl red. So let's continue. They say indigo is used to dye denim, a blue color, and coumarin for 40 is used to generate blue light in lasers. Both dyes occur naturally in plants but can be synthesized in the laboratory. So here we have the indigo and we have coumarin for 40 as the structure. So you expect that they're going to ask you about benzene chemistry when it comes to these kind of structures. Let's continue to the next page. The equation shows the reaction between a free radical, this one, and curcumin. So here they say shown by a simplified structure. So this is a simplified structure of curcumin. They say complete the left-hand side of the equation by adding curly half arrows. Here what we need to do is look at the product side and compare what you had at the reactant side. Imagine if I took away this. You can see that at the product side, these two combined, it means this free radical combined with another free radical. To generate a free radical from this side, it means that bond broke like that, creating a free radical, and then that free radical could have, the two could have combined to produce that, and then that would have broken like that, creating the free radical as well. So to take that away and to bring back this, you can see it's going to be like that. So this bond is basically breaks homolytically, creating two electrons going on different atoms within the bond, and then the structure is going to come like that. So this is what they were looking for. I'll continue down here. The isoselenide anions attached to protein side chains may undergo nucleophilic addition reactions with curcumin. Complete the mechanism for one of the steps in such a reaction, adding curly arrows to the simplified structures shown. Again, here what we have to do is look at the product side to be able to decode what happened on the right hand side. Here we can see this structure was alone. There is a protein and it has selenide. However, the selenide has a lone pair. How this selenide with its protein get attached onto this carbon, it means this lone pair formed a dative covalent bond to that carbon in order to form that bond. And then on the other side, we can see this double bond is no longer there, but it shifted position to there. It was here, but now it's there. It means it broke and moved to that position. And over here, we see there was a double bond here. There is no double bond here, but there is a negative, which was missing here. It means this double bond broke, returning the electron or the lone pair here, and then that became negatively charged. So this is very easy to see. You have to look at the product side to be able to decode how the reactant changed in order to produce the product. Let's go to the next part. Here it says curcumin anions can act as bidentate ligands in metal curcumin, like that, complexes. The oxygen atom of the curc ligand occupy adjacent coordination sites in the complex as shown. So this is the curcumin anion. They say complete the table relating to two MCUC complexes. Here they want us to see the coordination number is 4, and here we have 6 coordination number in that complex and in that complex. So here they ask us the oxygen M-oxygen bond. They told us its bond angle is 90. In this structure here, it is going to be 90 We do not say 180, it's going to be 90 because they asked for the oxygen metal oxygen bond. Oxygen metal oxygen bond, not anywhere else. So if you say 180, that will not be it. And then the shape, this is it's going to be square planar, as you can see, because this is bidentate. And again, to remind you here, they said this is a bidentate ligand, so the shape is going to be similar to something like that. And then here we have, this is going to be octahedral because, of course, we have coordination number 6 in the end. Since this one is bidentate, and then this is 2, and that is 2. So coordination number 6, we expect to be octahedral. The charge on the metal ion, this is going to be 3+, and that is 3+. So that's it, basically. If you want to know that, you just add up everything here. Remember, the anion is -1. So if you have -1, they're going to be 2. Yeah, this whole charge is 3. It means we could do, if I don't know the charge power, the oxidation state of that, let me call it X. And I know each of these is -1, so -2 is equal to +3. +1. So X is equal to 1 plus a 2, which is equal to 3. So the oxidation state of this metal, or the charge on the metal ion, should be a 3+. I will continue to the next part of the question. Part D, an incomplete synthesis for methyl red starting from 2-nitrobenzaldehyde and phenylamine is shown. So here we can see this is an aldehyde group because they say this is nitrobenzaldehyde, 2-nitrobenzaldehyde, that is the aldehyde group. So usually I like to break it down before I look at the question. So here, to convert an aldehyde group to a carboxylic acid group, we have to oxidize. So here we will use potassium dichromate acidified. And when we use tin with concentrated HCl, it means we are trying to reduce the nitro to convert it to an amino, so that's why we can see here. And then here we can see to form diazonium salt, it means we must have used nitrous acid, or at least you could have used sodium nitrite and dilute HCl to produce the nitrous acid, and the temperature should be below 5 degrees. Sometimes they accept 0 to 10, but I'll say below 5 degrees, and then we can produce this structure here. And when we go down here, we can see that they told us that we'll combine this and B to produce a structure down here. Since here we're beginning with phenylamine, it has a nucleophile. Reacting it with excess CH3I, it means there is going to be a nucleophilic substitution reaction here, whereby here we can see this lone pair on this is going to be donated to this carbon, and the iodine is going to be kicked out, creating a CH3 on that nitrogen. But since they used excess, it means both hydrogens on the nitrogen can be substituted. So excess, the first substitution kicks away one hydrogen, and the next kicks away the other hydrogen, as you can see this structure here, because they used excess. So we can combine that and that to produce the product. And again, to remind you, you cannot just guess this. You look at the product here, we can see there are 2 methyl groups. How did they come to be on the nitrogen? It is because this was in excess, so 2 methyls replaced the 2 hydrogens here, and then to form this structure, and that structure and that reacted to form the final product, which is going to be methyl red. So this is just a breakdown of it. Let me go to the real question. They said, state the reagent and conditions needed in step X. Step X is about oxidation. We will use acidified potassium dichromate, or you can say potassium dichromate and sulfuric acid, and then we heat under reflux so that the reaction goes to completion. A carboxylic acid is formed. Then the next part, they say, draw the structure of compound A. Compound A, you remember, it is when the carboxylic acid was formed, and then there is reduction that had occurred here. So again, to take you back a little, compound A is that. You can see the carboxylic acid having an NO2, reduction of the NO2 creates an amine. So that is why we have the amine here. Continue down here, they say, state the reagent needed for step Y. To take you back at step Y, just a minute. Step Y is this step here, conversion of to form a diazonium salt. We have to use sodium nitrite with HCl, or you could say nitrous acid. However, if you look at the question, they said reagents, so it has to be plural. You said sodium nitrite and hydrochloric acid. Those are the reagents, plural, they're looking for. And finally, draw the structure of compound B. Remember, to generate compound B, they used excess iodomethane And then, so it means each of the hydrogens here is going to be substituted as the reactions take place, as the nucleophilic substitution reaction takes place. And then we see that we produce this structure here. Down here we see they say the temperature used in steps Y and Z are kept as close to 5 as possible. State why the temperature should be neither higher or lower than 5. So if the temperature is higher than 5, then the product is going to decompose. The diazonium salt will decompose, forming phenol, nitrogen, and water. As you can see, I wrote something here. It's going to form phenol. This is the decomposition. So this could react with that, and the product form could decompose, creating a phenol, nitrogen, and water. However, if we react, the reason as to why they react at temperature not greater, not higher, I would say not less than 5, it is because we want the rate of reaction to be kept high. If you work at lower temperatures, the kinetic energy possessed by the reactants is going to be slower. The chance of having successful collisions is also going to be minimized. So to increase the rate at which successful collisions are occurring, we need more kinetic energy present, and that can be provided if the temperature is appropriate for the reaction to proceed. Indigo tin can be synthesized from 2-nitrobenzaldehyde and propanone in aqueous sodium hydroxide. So this is the structure of indigo tin. They say complete the equation for this reaction. So when you look at this structure, we can see, look at the reactant side and how this is turning into that. It looks as if 2 of these, so they've given us the 2. However, each of these is losing 2 oxygens, or total is going to be 4 oxygen atoms lost from this information of 2 of these. So we can see, since we have water this side, I can put 4 to represent the 4 oxygen atoms. And when I do that, I can also see here we have sodium hydroxide. And since this part here from sodium hydroxide ends up here, it means I don't have to incorporate it anywhere. So this part here ends up here, somewhere here. And that means if these ones are going to be 4 here, the hydrogens have to be taken into account to create the 8 hydrogens we are looking for. And this side is going to be putting a 2 here. Here we're going to put a 2, and that we put a 2 because you put a 2 here. That should also be a 2. And because you have a 2 here, that is also going to be a 2 to account for twice the sodium hydroxide that has been used. Now the next part says, calculate the mass of 2-nitrobenzaldehyde required to make 10 grams of indigo tin from this reaction when the percentage yield is 85%. You have to remember that percentage yield, let me use this, percentage yield is actual yield divided by the theoretical yield times 100. So if I'm given the percentage yield to be 85, it should equal to the theoretical yield given to me as 10 grams. Remember, this is the mass we desire to make, actual mass, so 10 grams, divided by x, the theoretical mass, or yield, times 100. And in the end, when you make x the subject, I get 11.765 grams as the theoretical mass. That is the theoretical mass of the product. So I will begin with that, dividing through by the molar mass to find the number of moles of indigo tin. So this is theoretical number of moles of indigo tin are going to be that. This is going to be moles. And then when we look at the mole ratio, it's 1 to 2. As you can see, if it's 1 to 2, it means the moles of indigo tin are good. Indigo tin to 2-nitrobenzaldehyde is 1 to 2. So the moles of 2-nitrobenzaldehyde is twice the moles of indigo tin, which gives us 0.089807 moles. I better put mole here and mole here so you guys can see the units. Now that I have the moles of 2-nitrobenzaldehyde, I can find the mass of 2-nitrobenzaldehyde, which will be in number of moles times molar mass. And this is going to be the moles times 151, which is the molar mass of 2-nitrobenzaldehyde. And in the end, I get 13.56 grams. So that is the mass we were looking for. Allow me to go to the next part. Here we see they say, give the structure of the organic product of each of the following reactions of coumarin 440. So here we can see they've given us this structure, but what we can see, there is an ester group here. Let me erase for you so that you can see properly. There is an ester. You can see this part here. It shows an ester. So they say hydrolysis with excess aqueous sodium hydroxide. Guys, when you see this, this is alkaline hydrolysis. And again, remember, esters can be hydrolyzed in acidic conditions or in alkaline conditions. When you do hydrolyze an ester in acidic condition, you produce a carboxylic acid as well as an alcohol. However, when you do hydrolysis in alkaline conditions, you produce a carboxylic salt and an alcohol. So in this case, we are going to produce a sort of a carboxylic acid or carboxylic salt and then an alcohol. So breaking the ester, again, remember the part that came from the carboxylic acid is going to be the part that becomes a carboxylic salt. So we expect this bond to break from here. And that part will go to the carboxylic acid, forming the carboxylic salt basically, while this part here is going to become the OH or forming an alcohol, as you can see this thing here. So here they said hydrolysis with excess aqueous sodium hydroxide. They wanted us to, okay. So I wrote this structure here, as you can see, because the reason for that is they said excess. If they just said sodium hydroxide, this structure here would be okay. However, when you use excess sodium hydroxide, this part here too is going to be substituted. The hydrogen can be kicked out by the sodium to produce ONA, as you can see. So the structure is going to be different, creating a structure similar to this. That is why I say that. And again, you have to read through some of the notes I've written here. If it was just normal without excess, you could produce a structure like this. But because we used excess, the sodium is going to replace the OH, kicking out the hydrogen and remaining. So the oxygen will remain, but the sodium is going to bind onto the oxygen, producing a salt, you can see here. And then on the other side, we'll have that. So the structure will be like that, or this is going to be replaced by a sodium as well. This is basically it, this. In drawing it to be in that same form. So the next part here, we see condensation of ethanol with ethanol chloride. Condensation reaction, it means smaller molecules are being lost. So when condensation occurs, this is the structure that we're going to form, because we know ethanol chloride will attach onto the NH2. Remember, it's going to be like ethanol chloride. So it's going to be like a nucleophilic substitution reaction, whereby this is partial plus, partial minus. So this partially positive carbon is going to receive electrons from the nitrogen in the RNH2, and therefore a nucleophilic substitution reaction will occur. If you can look at this part here, I showed you how it's going to be. The RNH2, this is a lone pair on the nitrogen, comes and binds here, and then that bond breaks. Then later, that comes back, and this one goes away, producing something that looks like this, and that is an amide. So the structure we are looking for is an amide, as you can see, this one here. A condensation reaction, HCl has been lost. So this part here is going to lose a hydrogen, and that part is going to lose the Cl, so HCl is lost. That is why we call this a condensation reaction. So this brings us to the end of section C. Thank you for being with us throughout this video. And please do not forget to subscribe to our channel. We'll keep bringing you very educative videos explaining various topics as well as many past papers. Please remember to check through the description box to see the links to section A as well as section B of this paper. See you in our next paper. Bye-bye.